Morning, guys. So this is a continuation of the last couple lessons in the energy option. If you do have questions from earlier sections, feel free to ask me during my office hours or just leave a question on Teams. I know majority of you are going to follow Mr. Sabari for his notes when he does review, but do note that you're more than welcome to ask any questions at any time. So I did want to finish off the sort of last two sections with you here. I'll post these notes here on the website. Again, hopefully you still have access to the Energy Google folder. I'll provide a link there as well. I'm going to mainly talk about C6 here on electrochemistry, on different types of batteries. I might end up separating this into two lessons, where the first part just overviews some of the general ideas, what are the types of questions that you might see, and then we'll actually leave the math to another lesson. So this one here is C6. It does have in the backing the redox chemistry that we've been doing, electrochemistry. It is going to recap with you some of the E-cell calculations, some of the terminology like oxidizing, reducing agents, gain of electrons, oxidation state, things like that. But really, if you look as a whole, it's not going to get into the nitty-gritties. It's not actually going to talk too much about electrolytic, talk too much about salt bridges and whatever, but this is more so a general comparison. What are the batteries that are currently out there? What are some of the advantages for some batteries over other batteries? What are some of the reactions that take place? And in that case there, they would just quote, here are the reactions during the discharge, here are the reactions during the recharge. We'll see a few pictures of that. Looking at some sample past papers, their favorite question in this section will be compare the different types of batteries. What's the advantage of, say, a lead acid battery in a car versus your lithium ion batteries in a phone? And it's more a broad stroke of this electrochemistry. So if redox chemistry wasn't your favorite, just hang in there. Fortunately, at least in this section, it's not going to be super technical. So with that in mind, let's just have a look at C6. So based on our redox chapter, our electrochemistry here, all the cells that we've been talking about have been what are called primary electrolytic cells. Again, with the new language here, we're going to call electrochemical cells voltaic cells. Voltaic cells use spontaneous reactions. The chemistry ends up providing electricity for you. Right? As the chemicals naturally react, you end up being able to taper off that current. Voltaic cells are also sometimes called a Daniell cell. These ones here will definitely be during the discharge of the battery. When we do a recharge, that's more so the electrolytic stuff, just to force the reactions going backwards, to refresh the chemicals that we have so that we can end up recharging the battery. Let's just take a look at some of the main components of a primary electrochemical cell. I know it's been a while. For an electrochemical cell or voltaic cell, we typically would expect to see two beakers. Because the reaction is spontaneous and I need a way of tapering the electrical energy, I need to have half the reaction occur on one side and half the reaction occur on the other. Most of the reactions in chapter 9 have been aqueous, so we had a solid metal plate as our conductor sitting inside a solution. When we start thinking about designing like AA batteries or 9-volt batteries, maybe using an aqueous solution is not such a good idea. If I start orienting the battery in different formation, it might end up affecting how the electrons interact. So I know, for example, in a AA battery, instead of using an actual aqueous and a liquidy electrolyte, they actually use a moist paste. It's basically the same chemicals, but it's absorbed onto almost like a pasty material, which is very porous, but at least it doesn't have the problem when you knock the battery over, it doesn't suddenly change the surface area, it doesn't change the orientation, ideas like that. So there are some engineering kind of aspects to this as well, but we're going to focus mainly on the main terms. So if you happen to know which is anode and which is cathode, typically we like putting the anode on the left-hand side, the cathode on the right-hand side. Our acronym is ANOX caret. So the ANOX part here says at the anode is the site of oxidation. Oxidation, Leo the lion says grr, oxidation is the loss of electrons, whereas reduction is the gain of electrons. So anode is the site of oxidation. It's the location of where oxidation occurs. It's the location where things start losing electrons. It does not necessarily have to be the plate itself. We've seen in chapter 9, the plate could be carbon or platinum. It could be completely inert. Maybe it's other chemicals that swim to its surface, lose the electron on the surface, become other things. But because that's the location of where the losses occurred, we can still call the metal conductor not only an electrode, but you can call it the anode. Electrons in an electrochemical cell always flow from anode to cathode. Remember, we're forcing the electrons to travel through a wire. It's through this wire where we actually taper off the electrical energy. Whenever electrons are in motion, in this case here it's going to be a direct current, we can actually taper off that energy. The anode for a Daniell cell here, the anode is going to be the negative part because all the electrons are deposited here. So the anode, as we're going to see on the next page, the anode is the negative electrode. The cathode is going to be relatively more positive, which is one reason why the electrons want to spontaneously go over to be picked up over here. And then typically we have analytes that end up solidifying on the surface. We talked about the mass increasing depending on the actual reaction itself. So we have the cathode. Let's just complete the sake here. Cathode is the site of reduction. It's the site where things actually gain electrons. A little bit weird to think about reduction as gain, but the things that we're actually taking actually have negative charges. They bring my charges, if I'm positive, closer to zero. If I'm already zero, into the negatives. Because we are dealing with electron transfers and charges either becoming solid or becoming ions, remember we need a salt bridge. The salt bridge, all it's there for is to maintain electrical neutrality. All it's there for is to counterbalance. The anions in the salt bridge will end up generally going to the anode to prevent this side from losing too much negative charge, whereas the cations will flow towards the cathode to keep this side here a little bit more positive. That sort of acts like an on-off switch in our lab, and we sort of were able to create the overall voltage. If you found during your lab the voltage was negative, it's just because when you did your voltmeter and you put the meter on one side and the other side, maybe you have it the other way around. Instead of electrons going one direction, you have it measuring the opposite direction. So positive and negative just has to do with where you put your leads. Those are the key ideas that we have from this section. As we look towards the different types of battery, we're going to see where the reactions actually take place for the lead-acid battery, for a nickel-cadmium battery, and whatnot. Again, the primary thing that they like asking is comparing the different cells one to the other. These cells, as referred to, are called primary cells. These ones here are, unfortunately, they're one-time use. They typically can't be recharged. There's now, when we're starting to consider being environmentally friendly, being economical here, there's now more push for designing what are called secondary cells. Secondary cells typically can last longer because they're rechargeable. You might know a rechargeable battery may not be able to fully get the same charge every time, but being able to use the same battery over and over again definitely extends the lifespan. So expensive at first, but a little bit more economical to use. A little bit of an intro to some of the terms that we'll see in this section. The electromotive force, we're going to call this the EMF. I think of the EMF as the true voltage your chemicals were supposed to be. So there is a certain standard reduction potential comparing to hydrogen and whatnot. There is a supposed voltage that these chemicals are supposed to give you. But because when we're manufacturing the battery, we're actually having to design where the wiring goes, what sort of components does it travel through, we're going to end up losing some of this voltage by the time we hit the terminals. So how this part would look like, let's say I have a AA battery, we have the positive terminal and the negative terminal. The true reactions are happening in here. That's providing a true EMF. That's the total voltage that I should have gotten. But as the electrons are sort of forced out of the battery, they encounter a little bit of resistance called an internal resistance as it travels through the battery. Some of the energy and some of the voltage is lost there. We use the Ohm's law here, which is I times R, which ends up saying the voltage at the terminals, the voltage that we end up being able to use, is going to be the true EMF, the true voltage from the chemical reactions, minus off a little bit of internal resistance. So that's the true EMF. That's what we've been calculating as an E cell. Some other terms here. So voltage, again, another way of thinking about it is the amount of energy that's given per charge. This is the push that causes electrons to actually travel out of the batteries. Current, as we know, is the flow of electric charge, so I is equal to Q over T. We saw in chapter 9, if we could figure out the charge, say the amount of current, and figure out how long the current has been turned on for, I know how many electrons have been transferred. It was just a simple mole ratio to get to, based on the number of electrons in the balance equation, how much mass ends up depositing on the electrode and vice versa. Resistance in general is sort of an impedance to current. It's sort of a slowing of the electrons. It's this internal resistance in the battery that causes a little bit of loss. There's also going to be resistance out here. If there was no resistance, you'd end up heating up this battery and causing a safety loss. In the chemistry, we are introduced to this concept of Gibbs free energy. I'll talk more so about the math of it in a later lesson, but Gibbs free energy, by definition, it's energy that's free. It's energy that is the part that's available for useful work. So say I have a battery, if I want to run an MP3 player, the amount of energy that the battery is able to supply in running the MP3 player is the Gibbs free energy. Now it is a little bit weird because of how we define energy zero. Energy zero is usually for charges that are infinitely far apart, they don't know each other present. That's where we define zero. So any charges in our sort of experience where they actually do see each other, all the energy values are going to be, at first will be negative. But even from then on, based on the battery itself, let's say from the start of the battery, all the chemicals are fresh. As the chemicals actually react, as reactants become products, as I lose my reactants, the Gibbs free energy will actually start changing here. As I produce more products, the Gibbs free energy might change. And depending not only on the delta G at first, whether it's spontaneous or not, but over time as the chemical molarities also change as well, as I lose reactants and as I lose the available free energy, as this one goes upwards, eventually we'll end up with equilibrium where I have a bare battery. Again, we're going to focus more so on the math in this part here later on, but just to show you, if I know delta G, and delta G here currently is negative, right? If I know minus, I'm going to show a more negative number minus a smaller negative number, overall is negative. This part means spontaneous. So this says the chemicals, when given the opportunity, they will naturally combine together and then they will naturally become products. Depending on how big this delta G value actually is, it's going to eventually hit the equilibrium mixture. If it's a reaction that goes to completion, this equilibrium mixture is fully pushed to the far right side. If it doesn't really go far away, sometimes equilibrium is somewhere midway as well. So we're going to hit some compromise. What you're going to find is there's always a little bit of a going up in free energy as we get to the products. It's always more spontaneous and more entropic when we have a mixture, which is why it's a little bit lower than, say, everything did become products, everything is all uniform, everything is all, they look alike, so they're going to end up being a little bit higher. Depending on the overall delta G, we're going to figure out where this equilibrium value actually is. I noticed there was a mistake on this lap here, on this sheet here. I talked about this terminal potential, the terminal voltage of the battery. I made a quick mistake here. So the terminal voltage here, if we can change this, the terminal voltage should be the true voltage, the true EMF from the reactions, minus off a little bit due to resistance. Because of that resistance, it's going to be unavailable for the charges to actually utilize. It's just wasted depending on how the charges actually are to travel through the battery itself. So as a second lesson, we're going to come back as we introduce a little bit more of the math. I'm going to come back to this section, so we're going to skip over it for a second. And just to finish off this lesson here, I just want to make just an overall comparison of the different types of batteries that we have. I have seen them ask on a paper 3 question, state the reaction for the discharge of this type of battery. Again, not the end of the world if you can't memorize it. They try to decrease the amount of memory or route regurgitation. What they want you to do is more so comparison. So towards the end of this section, you're going to see a general comparison. That's typically more questions that I end up seeing. So let's just go over these batteries here. Again, this is just a very broad stroke. Your textbooks have given you all the details in these reactions here. In this case here, we have a lead-acid battery. We have a reaction as an overall, it's broken up into 2 different types, oxidation and reduction half reactions here. This one here is sort of like a disproportionation reaction. A disproportionation reaction usually has, in this case here, let's say lead has an oxidation state. This one here, actually, it was a 0 and it's becoming a +2. In this case here, the forward reaction implies an oxidation, whereas the lead here, which is a +4 charge, implies a reduction, but to that very same compound. So it's an oxidation reaction, and we managed to taper off some of the voltage from this set. This part here is during the discharge cycle. This part here is when the battery is just running spontaneously. This is what's ending up happening. And this ends up forming a solid PbSO4 electrolyte. If you end up wanting to recharge your car battery, what you're going to do is you're going to plug into some external voltage source. The external voltage source electrolytically can force these reactions back into the original fresh chemicals, maybe not 100%, But once we have fresh chemical again, the chemicals can spontaneously come back and become PbSO4. The nice thing about this cell here is PbSO4, if you notice the state of it is solid. Being solid, it is not dispersed into the electrolyte. So let me see if I can pull up a quick picture for you to sort of imply this here. Okay, so if I can just pull up a quick, this one here is the car battery picture. So we have the two different electrodes. We have the anode and we have the cathode. If you look at those reactions in detail, you're going to see PbSO4 is a solid that ends up forming on the left side and forms on the right side. This PbSO4 ends up as a deposit. It ends up coating both of the electrodes, and it ends up decreasing the surface area between the electrode and the electrolytes in the solution. So over time, during the discharge, you have PbSO4, it's insoluble, it doesn't leave, it doesn't jump into solution. During the recharge cycle, we basically want to remove some of that PbSO4, refresh some of the surface area on these plates here to actually get some more reaction going. So that's how a car battery works, both the charge and the recharge. We'll come back to some of those pictures later on. Another common type of battery that we have here is a nickel-cadmium battery. We're going to use potassium hydroxide as the electrolyte. It's happening to now. Sorry about that. So, nickel-cadmium battery here with the basic electrolyte. Again, they give you the overall reaction. Not super important for you to memorize the entire equation. They separate for you. Here's the loss and here's the gain. Those are the two half reactions. You would, in chapter 9, need to balance it. Lowest common multiple between electrons and canceling electrons and all that. But again, what they're saying here is discharge is one way, and when you end up recharging, you're electrolytically forcing these guys back into the early reaction. I think these reactions as listed here are actually the recharges. This ends up taking the nickel hydroxide that we got from earlier and reforming this complex here, as well as the cadmium hydroxide and reforming cadmium. They introduce this term here called discharge memory. Basically, even though these reactions are reversible, nothing's 100%. Even with our earlier reaction when we're like, oh, we produce all this solid PbSO4, there's no guarantee that the PbSO4 all ends up breaking up in the correct areas. When it reforms the lead and when it forms the PbO2, there's no telling that maybe the surface area is different, maybe it's a little more powdered than it was before. Typically, over time, the battery, through wear and tear, doesn't last forever. So just keep that in the back of your mind. That's referred to as a discharge memory. Most of our phone batteries and maybe computer batteries are lithium-ion charged or lithium-ion batteries. So lithium-ion battery is just actually this picture on the left-hand side first. Nice things, some advantages to lithium-ion. It's a very low-dense material. It's a very highly reactive material, so although it does cause safety precautions, things like that, we should be able to get a lot of energy using a very easy material to work with. So again, what's happening here is we have a discharge. We have the two equations for it. It's called a lithium-ion battery because lithium as a metal ends up becoming lithium ions, dropping off the electrons. Instead of, like I mentioned, using a salt bridge or aqueous solutions, we probably use a gel of some material. We allow the cations and anions to pass as they need to, but we somehow force the electrons to have to travel through an external wire. So, yeah, this one here is our lithium-ion battery. There's a lot of talk about this fourth one here, which is a hydrogen fuel cell. We have a sample picture of it on the right-hand side here. So this bottom one here is for hydrogen fuel cell. The nice thing about a hydrogen fuel cell is if you look at the chemistry, we're using plain old hydrogen and plain old oxygen as our reactant. These are the things that are going into it. And the only byproduct out of this reaction is just water. Very, very environmentally friendly, very economical for use as well. So not only is this reaction here exothermic, it ends up giving off energy. If we can harness this energy properly, likewise, we can have electrons traveling through an external circuit. We can then taper that electrical energy as we need. And we have a proton exchange membrane, they shorthand that PEM. This one here acts like the salt bridge. This salt bridge here can either act in either alkaline, in a basic solution, or an acidic solution, and they've given you, notice that both of the equations are actually the same balanced equation. However, depending on which catalyst, depending on what's actually in this proton exchange membrane, in alkaline or in basic solutions, hydroxide is present in excess, whereas in acidic, H+ is present in excess. The H pluses do end up canceling out, hydroxides end up canceling out, so the same overall. But if you were an engineer and you were designing these cells, it might be good for you to actually figure out, well, do I want it positive or negative, so on and so forth. We're going to come back to measure this concept here called thermodynamic cell efficiency. I'll show you a numerically worked out example afterwards, but pretty much what they do here is they compare the delta H here is sort of the endo and the exo of the reaction. This is how much energy, this is how much heat that was transferred. Let's compare that to how much free energy that I have out of the total amount of energy that was transferred. I'm not too sure why they put a negative and negative. Maybe it's because they're expecting free energy numbers are going to be negatives themselves, delta H's are going to be negative themselves, but either way the negatives cancel out, so your efficiency ends up as a positive. Again, I'm going to show you how these calculations are worked out, but you see based on it could be the very same reaction. In this case, the only difference is liquid and gas, but the efficiencies are wildly different. So definitely we want to get most bang for our buck. If we have a choice and it's economical, we definitely want to have the high efficiency case over the low. There's a few last battery cells here just to finish off this lesson here. We have a direct methanol fuel cell, the DMFC. Methanol is nice because it's a very nice stable liquid to work with. We already saw it being used in sort of biofuels in an earlier section. In this case here, it represents the combustion of methanol, so CH3OH and oxygen, the burning of it. Again, they separate the anode and the cathode reaction for you. It's not just hydrogen as a fuel cell, we can even use methanol as a fuel cell. And depending on how you set it up, sometimes the efficiency of this may even be comparable to a hypothetical hydrogen fuel cell. And then just another example of fuel cell on the last side here, a microbial fuel cell. This one's interesting in the fact that we actually use microbes, living organisms, to actually participate in the loss of electron reactions or gain of electron reactions. The bacteria actually act as the chemical catalysts or enzymes that actually allow the reaction to proceed quick enough. So we have a microbial fuel cell here. I'll show you a quick picture of this afterwards. You'll notice terms here. On the one side, we're going to do anaerobic. Anaerobic means no oxygen. We're going to design that side so no oxygen gets to it. Whereas on the other side, maybe we need aerobic, where we need oxygen. As you can imagine, that would take a little bit of engineering too. As I was mentioning, this section here is sort of a broad stroke. Okay, it doesn't necessarily need you to memorize every single equation, every single what's the oxidation reduction for these types of cells. They really like asking you this last section here, what are the general advantages and disadvantages to each of the cells? Let's just go over briefly here. Lead acid battery here, we have, say, a car battery. Okay, it's able to provide huge amounts of energy over short periods. But if you look at the reactions, we're dealing with things like lead, we're dealing with things like sulfuric acid as an electrolyte. All of those contribute to pollution, so things to keep in mind, especially when there's going to be so many cars on the road. We have nickel cadmium as a battery. They say just experimentally it's a longer life than the lead acid battery than the typical car battery. But since we're starting to use heavy metals like nickel and cadmium, at least the cadmium is very toxic, so there needs to be enough safety sort of design in it. It tends to be very expensive as well, so economical also becomes an important consideration. Lithium-ion batteries, like I mentioned, for your phones and computers, low density, very high voltage, no toxic materials, so that's environmentally very nice, but again, very expensive and typically very limited lifespan overall as a big comparison. And then there's a big push to get to fuel cells. Again, the really nice thing is, let's say hydrogen fuel cell, we're just here to use hydrogen and oxygen as really simple raw materials. We're going to taper off the electrical energy as we need, and the only byproduct ends up as water, which is fairly environmentally friendly. Hydrogen, as you know, has a disadvantage, however, it's very flammable, so especially when batteries tend to get hot, it can tend to be an explosive hazard. If you're ending up producing tons and tons of hydrogen and oxygen, you need to also worry about the way of transporting and storing it safely enough so that the plants can deal with it. The plants can actually take all the raw material and effectively and efficiently utilize the material. So I just want to flip through a few last pictures just so that you have a general comparison of the different batteries themselves. And then as a separate lesson, I'm going to show you a little bit more of the math. We'll go over how do we get the thermodynamic efficiency calculation, as well as a little bit of this delta G calculation from our. So pull up a quick PowerPoint here. Here's a few quick pictures just to supplement our lesson. We talked about sort of this is a zoom in on the one side of the electrode. In this case here we have copper ions. As a cation, it's moving towards the cathode. So I would imagine this is the reduction plate. That's confirmed by the fact that electrons are actually arriving here. The copper ions pick up the electrons. They typically solidify on the surface. Not only does that increase the amount of mass of the electrode itself, it also tends to decrease the positive charge, which is why in the salt bridge it actually needs to maintain that positive charge on the right hand side. We talked about an internal resistance. There's a nice picture for it. We're using the V0 as a symbol for the true EMF. The actual voltage my chemicals should have given me, but as the chemicals end up traveling through the bulk material of the battery itself, we end up losing I times R, a little bit of that free energy due to the internal resistance. Here's a typical picture of a redox cell. Again, if you happen to know which is the anode and cathode, conventionally we typically put anode on the left side, cathode on the right side. Keep in mind electrons only travel through the wire. Electrons never jump into solution. The only things moving around solutions are your salt bridges and your ions. Again, any anions that I have, they tend to go to the anode side. Any cations that I have tend to go to the cathode. Depending on the cotton plugs that you put on the ends of these salt bridges, sometimes even these cations can actually go upward. But even if they couldn't, if their size isn't working out, you can actually use the ions of the salt bridge, typically something that's low reactivity, really poor oxidizing agent, reducing agent that doesn't interfere with the rest of the reaction. We're going to come to this equation here as what's called the Nernst equation. In chapter 9 we've been mainly dealing with everything at standard state. If you can just remind yourself what standard state is. 1 bar pressure, typically 298 Kelvin. When we dealt with solutions, the molarities have been 1 molar, especially as batteries are running and they start using up chemicals. There is a sort of correction term and we can figure out what's the voltage at any given time, especially when we're no longer at standard state, especially when the molarities are a little bit lower. Here was that car battery as we mentioned from earlier, and then we'll have another picture look at a few of the other cells. This one is just a typical look at that car battery again. They engineer it in different segments, right? Different casing. Remember the interesting thing here is the PbSO4 is a solvent. It ends up depositing on the sides of these surfaces. The recharge would just involve running the reactions backwards, forcing the PbSO4 back into the individual Pb and PbO2. So as you started seeing here, we're not doing a lot of the detail. We're not having to balance these redox reactions ourselves, lowest common multiple, things like that. But at least you should remember, say, oxidation state. Oxidation state of lead here is 0. Over here is +2. So 0 becomes +2 oxidation. So you should still be able to identify those things, even if you're not directly given the half reactions. Last few cells here, we have a nickel-cadmium battery. Again, these are potentially very toxic materials, but you have the reactions. Careful when they list reactions, whether they're talking about discharge or recharge. Discharge is the spontaneous. This is when electrons are actually used for electrical energy. If it's recharge, you're using an external source to actually run the reaction backwards. Here's that picture of the lithium-ion battery again. So we have lithium on one side, we have a gel-like material for the salt bridge, electrons are forced through the wire, and that's where we taper off the electrical energy. And the last couple here are the fuel cells. We're going to punch in hydrogen and oxygen as our only reactants. We're going to somehow set it up so the electrons still flow through the external circuit. That's where we taper off electrical energy. This is being run in an alkaline solution. We saw reactions of it being done acidic. I think there's a picture of it on the back side. And the nice thing is the outcome is just water, very, very environmental. I think the next slide here shows you the same reaction, H2NO2, but this time in acidic conditions. This is where that notion of efficiency will become important. The more efficient it is, it's going to make it more likely that we're going to use that. And lastly here, this one here is just the reactions for the methanol fuel cell. So methanol burning in water, also in basic solution. I wanted to show you a picture of that bacterial fuel cell as well. We talked about the one side being anaerobic without oxygen, the other side being aerobic. You'll notice that we've actually absorbed actual microbes, and these ones here are the catalysts and enzymes to allow the reaction to occur, to allow for the loss of electrons, and eventually using that electrons as electricity. What's the advantage here is looking at the raw ingredients. We're just using wastewater, water that's contaminated, which otherwise would be tossed out, and we're able to feed that to the bacteria, which harnesses those chemicals and actually generates something good out of it. Oxygen is the other reactant, so definitely this side will be aerobic, so a little bit of engineering to design both sides. So again, I'm going to do math as a separate lesson, but there you go as a general overview of the different batteries. If you have any questions, just let me know. Thanks, guys.